All right, let's look at the questions I assigned for section 1.1. So for this question 6 here, so we have a differential equation, y prime, and we are offered the solution for it. So what we're asked to do is to verify it. So we can do that through direct substitution. So if this is an expression we have for y of t, then we can take a derivative of it to get y prime of t. So what is the derivative of negative 7 e to the t squared? That'll be, so derivative of any exponential function contains the original exponential function multiplied by the derivative of the exponent. So the derivative of t squared is 2t. Simplifying gives me negative 14t e to the t squared. So now I have an expression for y prime. So now let's do this. Let's plug everything into this equation, our original differential equation, and make sure it all agrees. So y prime is negative 14 t e to the t squared equals 2t times y, which is negative 7 e to the t squared minus a half plus t. Nothing really to simplify on the left-hand side, so we'll manipulate the right and see what happens. Distribute this, I get negative 14 t e to the t squared minus a half times 2t, so minus t plus t. These cancel. So, yep, I feel good about that. So both sides agree. Negative 14t e to the t squared. So yeah, that's indeed a good solution to that differential equation. All right, moving on. So we have a differential equation, y prime equals y times 2 minus y. And again, want to verify that the solution they're giving me here is valid. So again, we can take a derivative. So what is y prime of t? Actually, let's do this first. Let's rewrite the solution given. So the solution they're offering is 2 over 1 plus c e to the negative 2t. I'm going to rewrite this as 2 times 1 plus c e to the negative 2t, that quantity all to the negative 1. So if I take a derivative, I get y prime of t equals negative 2 times 1 plus c e to the negative 2t to the negative 2. But then I have to multiply by the derivative of this inner function to follow the chain rule. So that becomes negative 2c e to the negative 2t. All right, cleaning this up a little bit gives us negative 2 times negative 2, positive 4. C e to the negative 2t over 1 plus c e to the negative 2t squared. All right, so this is an expression I have for y of t. Oh, I'm sorry, y prime of t. So why did we do that? We were asked to prove that the differential equation I have, or sorry, the expression I was given for y actually is a solution differential equation I was given. So now we can substitute this. So y prime, which is 4c e to the negative 2t over 1 plus c e to the negative 2t squared equals y. What is y? 2 over 1 plus c e to the negative 2t times 2 minus y. So 2 minus 2 times 1 plus c e to the negative 2t. All right. So it looks like the left-hand side is not really Yeah, I don't really want to mess with the left-hand side too much. So with the right-hand side, what manipulation can we do to see if they agree? Um, so we have some choices here. What I am going to elect to do is I'm going to take the two terms inside the parentheses, find a common denominator, and add them together. So 2 over 1 plus c e to the negative 2t times 2 times 1 plus c e to the negative 2t minus 2 all over 1 plus c e to the negative 2t. All right. If I start simplifying some stuff in here, what do I get? Well, if I expand this or distribute here, I get 2 times 1, 2. That's going to cancel the negative 2 on the outside. So what I'm really going to be left with on the inside here is this. So I'll just carry the term on the outside, 2 over 1 plus c e to the negative 2t times, what did I say it was? 2c e to the negative 2t over 1 plus c e to the negative 2t. All right, do I believe this is the same as the left-hand side? Well, the denominator is 1 plus c e to the negative 2t squared. I believe that my denominators are going to agree because I have 1 plus c e to the negative 2t in both denominators. If I multiply them together, they're going to be squared. And then what is 2 times 2c e to the negative 2t? I believe that is indeed 4c e to the negative 2t. So I feel good about the solution offered here. All right, sketching solution curves. Let's go ahead and take a look. I'm going to go ahead and back out and go look at Desmos. Go away, Zoom. So 2 over 1 plus CE to the negative 2x. And yes, I'll add a slider. So if this is not something you were aware that you could do in Desmos, you can insert a constant into an equation and basically dial in values of it. So what values do I care about? I care about 1, 2, and 5. So when c equals 1, we have a curve that has this profile here. Let's think about what would happen if I make t larger, or sorry, c larger. So our numerator is a constant 2. So basically what's happening with our function here? We're going to be dividing 2 by 1 plus c, which if we look back to the question as written, I'm really only looking at positive values. So 1, 2, 3, 4, and 5. Because of that, okay, so c is only going to be positive. This is an exponential term. If you raise a positive number to a power, I don't care what that power is, negative or positive, that's only going to be positive. So essentially what I'm doing here is I'm dividing 2, a positive number, by a positive number. So what's going to happen as c gets larger? Basically, I am making the denominator larger. So how would I expect this function to behave if I make the denominator larger? I would expect the overall value of the function to get smaller. So let's see if that follows suit if I slide the value of c up to 2. Actually, we can just, yeah. So we see these values of y start to decrease. And I know this is not exactly what you were asked to do, but this is the kind of response we're seeing. So Let's do this. Let me go ahead and copy this. Like that. 3, 4, 5. And I'll replace C with the values we care about. Sliders are all well and good, but let's actually look at them all side by side. So if we kind of zoom in to see like these responses here, the largest one here should be where C equals 1, then the green should be where C equals 2, and so on and so forth. So basically what the increase in the value of C basically diminishes this initial behavior of this curve. You're still going to have, as you look out to the right here, we're still going to have a function that increases and approaches 2, but it's a matter of how rapidly does it approach 2. Okay, so let's look at the final part of this question. Verify that y equals 0 is a solution to, oh, no, go back. Verify that y equals 0 is a solution to the differential equation in part A. So that should be quick to do. If y of t equals 0, that means y prime of t equals 0. So yes, if I plug those things into my equation, I get 0 equals 0 times 2 minus 0. Yes, that checks out. So y equals 0 is a solution to this differential equation. But if we look at our equation here, can you find a value for c such that 2 over 1 plus c e to the negative 2t equals 0? I don't know. Let's try. Let's try to isolate c in this equation. So 2 over 1 plus c e to the negative 2t equals 0. Let's clear the fractions. So I'm going to multiply both sides by 1 plus c e to the negative 2t. That gives me 2 equals 0 times 1 plus c e to the negative 2t. I already have something that's nonsense. So that already tells me that it's impossible to make this happen. Yes, y equals 0 is a solution to the differential equation, but it is distinct from the solution that we gave in part A. All right, let's go ahead and look at number 28. Okay, so now we're given some descriptions of a situation, and we are going to write some differential equations based on those descriptions. So the growth of a population of rabbits with unlimited resources in space can be modeled by this exponential growth equation. So this is a pretty unrealistic way to think about this. They're going to run out of space. They're going to run out of food. They're going to, be hunted by predators. There's going to be something that prevents them from growing without bound. Okay. So let's look at these different changes here. A, write a differential equation to model a population of rabbits with unlimited resources where hunting is allowed at a constant rate alpha. By constant rate, I'm going to assume that, all right, every year, alpha rabbits are going to be hunted. So every year, the population of rabbits is going to decrease by alpha rabbits. And if that's true, then we can subtract KP by alpha. So let's give it a value. Let's say alpha is 100. Hunters are going to kill an average or kill a constant 100 rabbits every year. So after year 1, how many rabbits are going to die as a result of hunting? 100. After 2 years, how many are going to die as a function of hunting? 200, and so on. Let's do one more. After 3 years, how many are going to be hunted? 300. So that's a linear rate. But it's a linear relationship, which is equivalent to saying the rate of change is constant, which is why when we think about our differential equation, that rate is a constant. It's simply a number. All right, moving on to part B, write a differential equation to model a population of rabbits with unlimited resources. So that part is dp dt equals kp, simple exponential growth, where hunting is allowed at a rate proportional to the population of rabbits. So now it's not a constant rate. So basically, I'm going to allow the more rabbits there are, the more hunting I'm going to allow. So, and more specifically, it's proportional to the number of rabbits there are. So let's say alpha is still the amount of hunting that's allowed. Now I'm going to multiply it by p. So kp is the amount, kp is essentially the birth rate. How many new rabbits are there going to be every year? And alpha p is the death rate. Or not the death rate, it's just the number of rabbits that are going to be lost to hunting, or the rate at which they're going to be lost to hunting. Now that rate is variable. It's governed by how many rabbits there actually are at any given time. All right, part C. Write a differential equation to model a population of rabbits with unlimited resources. All right, pause there. dp dt equals kp. Try writing k. There you go. Where hunting is this different? Limited resources. Oh yeah, read. Okay. So what does limited resources mean? So we're going away from the logistic growth. Away from exponential growth into the logistic growth model. So yes, what does the rate of growth of population have to do with? So yes, it depends on what the population is. So that's the KP component, but it also depends on how close are we to the carrying capacity of our habitat. So I have this other factor. So if our population is very near zero, the growth will be small. But if our population is very near this number n, which is the largest population that our habitat can sustain, our growth will also be small. So this right here, this is our logistic model. This accounts for the fact that our population will grow with some kind of, upper limit. All right. And then we're bringing our hunting at a constant rate. We've already kind of talked about how to represent that. That's going to give us a rate of negative alpha. All right. And then finally, part D, write a differential equation to model a population of rabbits with limited resources. Okay. So again, we're starting with the logistic growth model, Kp times 1 minus p over n, where n is the carrying capacity, where hunting is allowed at a rate proportional to the population of rabbits. Okay, so we have all the ingredients. Now we're just kind of mixing and matching them. So the hunting rate is alpha, but now it's not a constant rate. It is a constant of proportionality that joins, or that is multiplied by the number of rabbits there are. So as far as we can, there's a lot of constants we don't know the values of, but as far as we can, these are how we can describe these differential equations.